I'm Zibi Turtle of the Johns Hopkins Applied Physics Laboratory and the principal investigator of the Dragonfly New Frontiers mission to explore Titan's organic chemistry. Why do we want to explore Titan? We can't go back to study our own prebiotic history here on Earth. So we look to other worlds in our solar system that offer clues to the chemical processes that may have led to life here on Earth. Titan is one of these worlds and holds keys to understanding our chemical origins. Titan is the largest of Saturn's 62 moons, the diameter over 5,000 kilometers. The surface gravity at Titan is about 1/7 that of the gravity here at the surface of Earth, and the atmospheric pressure is 1.5 times the pressure at Earth's surface. And this is what's so unique about Titan, is its atmosphere. The surface temperature at Titan, out in the outer solar system, is 94 Kelvin or negative 290 Fahrenheit. And at these temperatures, the bedrock composition is water ice. The atmospheric composition is primarily nitrogen with a little bit of methane. And that's what makes Titan such an important astrobiological target. The methane in Titan's atmosphere is what makes it a particularly valuable target from an astrobiological perspective. At the top of Titan's extended atmosphere, methane is broken down and the molecules recombine to form very large, complex carbon molecules. And these condense into hazes, and the organic material falls out and litters the surface of Titan, where it's had the opportunity in the past to mix with liquid water at the sites of impact cratering that will have melted the target crust, or even cryovolcanism. There's also water deep in Titan's interior ocean, under the ice shell. And there's also a second liquid in the system in the form of the active methane cycle, like Earth's water cycle, where methane forms clouds and rain and rivers and lakes and seas on the surface. And it's possible that liquid methane could support the development of alternate, exotic biological systems. So Titan offers a chance to look for answers to fundamental questions. What makes a planet or a moon habitable? What are the chemical processes that led to the development of life? And even, has life developed elsewhere in our solar system? So what we want to do is take what we've learned from Cassini and Huygens' exploration of Titan to the next step of in situ exploration with the Dragonfly mission. We know from Cassini where we want to look on the surface of Titan for answers to these important questions. They're diverse surface materials and environments with an Earth-like variety of geologic processes. And so the challenge is to be able to sample materials and measure the compositions in detail at multiple different locations. And that's where Titan's atmosphere really helps us out. Because with an atmospheric density 4 times higher than the density of Earth's atmosphere and gravity 1/7 Earth's gravity, heavier than air mobility is highly efficient, and it is much easier physically to be able to fly on Titan. So Dragonfly is designed as a rotorcraft lander. We have a cruise stage that will take us from Earth to Titan, and an entry vehicle that protects the lander as we come into the Titanian atmosphere, and then the rotorcraft itself, which is powered by an MMRTG, a multi-mission radioisotope thermal electric generator, the same power source as the Curiosity rover on Mars, and a totally self-contained unit which performs direct-to-Earth communication from a high-gain antenna on board. Dragonfly, because we can fly, will also be able to take measurements in flight as well as on the surface of Titan. Dragonfly's payload is designed to measure the details of the surface chemistry and put that in the context of the Titan environment. There's a mass spectrometer that's fed by 2 drills on either side of the lander that sample the surface material and bring it via pneumatic transport into the mass spectrometer. There's also a gamma ray and neutron spectrometer that allows us to measure the bulk elemental composition of the surface area beneath the lander. And then a geophysics and meteorology package that allows us to monitor atmospheric conditions, measure surface conditions, and even listen for Titan quakes. And then there's a camera suite as well with 8 science cameras, including 2 cameras mounted on the high gain antenna to take advantage of the articulation to be able to point and build up panoramas of the surface terrain surrounding the lander. Dragonfly is scheduled to launch in 2027 and arrive at Titan in the mid-2030s. We do direct atmospheric entry at Titan and descend down through the atmosphere at a similar latitude and the same time of Titan's year as the Huygens probe descent in 2005. When we get down to a few kilometers altitude, the heat shield is released and Dragonfly spins up the rotors and releases from the back shell to fly to our initial landing site in the Shangri-La Sand Sea, the organic dunes that encircle Titan's equatorial region. Our landing site near the Selk impact crater allows us to explore a region where the rich organic material on Titan may have interacted with liquid water in Titan's past. The primary science is to measure the chemistry of Titan to understand the chemical components available and how they may have interacted in the past, and then to put this in the context of the habitability of Titan's environment. The mission duration is about 3 years or 74 Titan days of exploration, traveling up to 100 miles or so across the surface. There are many advantages of Titan's environment that we can use to good effect. The dense atmosphere, of course, allows flight, but the dense atmosphere and long Titan days also mean the atmosphere is quite calm. So this is perfect for flying. The 16-day Titan day also means a more relaxed operations schedule that we can actually tailor to business working hours here on Earth. And the low temperatures outside the lander mean we can actually take advantage of passive cooling for components of the instrumentation that prefer cryogenic temperatures. The team has been very hard at work developing the mission design and doing testing of different hardware components in the Titan environment to make sure that everything will work together at Titan. And we have many opportunities that we've developed for participation as well, including student and early career programs, workshops at conferences, and a NASA Participating Scientist program. And we're looking forward to sharing the exploration of Titan and the development of the Dragonfly rotorcraft itself via augmented reality and virtual reality tools. Thank you.